Okay, we got everybody? I hope so. Okay, welcome to the March C++ users group meeting. We'll go through our normal, thanking our sponsors. Thanks to the City of Bellevue for sponsoring our meeting room and at least our marginally working projector. We'd like to also thank Cyberdata Corporation for sponsoring our Teams account. By the way, the other thing you can do is just join the Teams account and then just share directly. We'll only get one screen.
Thank you, Cyberdata.
We do have a code of conduct. It's the Bellevue City Hall Code of Conduct. It's kind of summarized there. If you really want to see the whole thing, it's presented on a nice plaque in the hall by the security guard. Let's see. So next thing I'm going to do is I'm going to hit the speaker topics survey results real quick. And just a quick note, we are booked here through mid-2026 and plan to stay here as long as we can. Mostly this is working out pretty well. Quick question for folks in the room and even folks online. We're talking about pizza a bit. I'm entertaining doing another pizza social later in the year. I think we can do that here. I've got to double check and make sure we can bring in food. I've seen it here before, so I think we can. How many folks are interested in that? If we, instead of a formal meeting, just getting some pizza and all chatting for a meeting? Okay, so pretty much, how about folks online? Is that something you folks would come in for?
Probably not.
Okay, I don't want to leave you out, but I don't have a way to fax you a pizza. And we've seen how the digital conveyor from Galaxy Quest works, and we don't want to do that either. Okay. So I'll look into getting that set up later in the year. Next one I wanted to go through, get that. Can folks see that okay? Or?
It'd be great if you could zoom in some. That's kind of small. That helps.
Good? Okay. That works. Okay, so as some of you may or may not be aware, we did a little survey earlier in the year to kind of get a feel for what people want to see. And we got 21 responses. We did this through SurveyMonkey, and you get 25 for free, so it worked out perfectly. This is a low budget survey. We'll qualify right there. So question one, which aspects of programming are you most interested in? Looks like language features, library features, and tooling are all pretty popular. Some other stuff in there. Let's see. Down here. Yep. So software diagnostics, telemetry, good algorithms, programming models. So that was, you know, kind of the same stuff. We've been doing a fair amount of that, so I don't think too much, it's not too much differentiating there. Next one, which programming techniques or tools or interests? Again, pretty much all over the board. Version control systems, well, I guess we'll just stay away from that. Nobody cares. They're important. Don't want to diminish it, but yeah. Machine learning and agentic coding. May have a couple more on that coming up pretty soon. I've seen a few there. Design patterns, version control. What did other people say? Oh, math libraries, HPC and GPU coroutines. We've done a few of those, so that's good. GPU and graphics. Yep, we got the CUDA stuff floating around. Lesson learned. That's actually an interesting one. Just crossed my mind. What do folks think? So remember we tried to do the lightning rounds, right? And that had kind of mixed success. What do folks think about doing a lightning round where people just come and share their bad experiences? Is that?
Can you include management?
Yes, I could include them, but they probably won't show up. Okay.
Issues with management.
Oh, no, yeah, let's stay out of that one. Okay, bad idea. Just random thought went through my head. There's no takers for that one, so we'll let it die.
I don't mind hearing about failures and lessons learned.
Uh-huh.
But I don't just want to hear somebody complain without a lesson learned.
Oh, right, yes, yes. It would definitely be a failures and lessons learned. Okay, let's see. What level of talks are you interested in? Beginner is kind of down there, intermediate and advanced. So we'll kind of stick to those. That actually did have a pretty solid bias to it.
I'd like to say that it might be good to have some beginner talks if we want new people to join our group.
Yes. Oh, yeah, none of these are by, let me just put the standard qualifier out there that I should have. None of these are hard and fast, and it's going to be somewhat dependent on what speakers I can get, because I'll take anything over an empty room. But this kind of gives me, the point of this was to kind of give me some guidance on what folks are interested in. So when I'm seeking speakers, I will bias toward the group interests. That's kind of where I'm heading with this. So we'll head toward intermediate and advanced, and yeah, we'll have some beginners too. Not to say we won't do any beginner talks, because as you point out, they are important. Matter of fact, even for people who have been in the industry for decades, the beginner talks are important.
Right, they might be beginning with C++, even though they've been coding Java for 20 years.
Or I'll just throw out, you know, when I've gone to the CPPCon stuff or any other conference, right? I will deliberately schedule in a 1 or 2 back to basics talks just for the refresher, right? Even if I think I know it, I always still pick something up, so. How abstract of a talk do you enjoy? Sounds like balanced and concrete, have a pretty clear dominance there. Okay, and let's see, what feedback or questions? Let's see. Okay, one person, haven't attended in person, always watch the recordings. Okay, that's cool. Meetings at City Hall sound good to me. Me too, since it's working. Let's see, plus these embedded systems. Okay, just general comment. That was it. So thanks to everyone. Oops, got somebody waiting in the lobby.
That's me.
Oh, okay.
Still not sure how I'm going to do this because I share my screen. I'm still not going to see the presenter view.
I might be able to put the. We'll try it again here in just a second. Okay, so thanks to everyone who filled out the survey, both here and online, and whoever that was. With that, we're having a little fun with the projector. So let's see what we can do about. We're going to take a small little break here and see what I can do about getting that working.
Have you experimented with the Windows P key?
Yeah, the thing is his laptop is not recognizing the projector.
Yeah, it says your PC can't project to movies. Try reinstalling the driver. Yeah,
Oh, okay.
it worked just fine.
Well, tell you what
2 hours ago.
Oh, it always does.
Apologies down.
Let's see. WCPP, probability and statistics. Let me just see if I can bring it up on mine. Okay, so I'm in open office. Do an F5 here real quick. Looks like animations are working.
No, I mean, but the presenter view.
No, I can deal with that too.
Presenter view on your laptop and present from Lloyd's.
Hang
You'll
on.
have to press forward at the same time, but it might work that way.
Actually, give me the HDMI. Because my laptop is being recognized by the projector. Okay. That's live. There's your presenter view and your other one.
Oh, wow. You are the man.
Okay, and I'll just switch seats with you. Okay, and with that, we'll turn it over to Dan, who's going to talk about some statistical stuff. Oh, geez, you plugged in a presenter mouse. Now that I don't know whether it's going to recognize.
What, this? Yeah.
Oh, perfect, it does. Sweet.
Yeah, okay.
You didn't just put a virus on my laptop, did you?
Yeah, you're gonna really enjoy it. Anyway, thanks, Lloyd, for coming to the rescue here. Okay, well, good evening, everybody. And so this topic is on probability and statistics in C++. I think most of you here know me. Some might not. So my background actually is in quantitative computing and specifically in finance. So the things that I'm usually present on and interested in regard math and C++. So just to look at things that we'll talk about, we'll start out by looking at the random number generators in the standard library. These were included beginning with C++ 11. Then we'll have a look at boost statistical distributions and functions. And then there are some newer and lighter weight alternatives to standard library random engines. And just a quick look at those. Also have a look at boost accumulators. And then we will we'll conclude with a look at a proposal for the C++ 29 standard, P1708, basic statistics, and the main author for that is in attendance with us online. So good to see you, Richard. Thank you very much. Okay, so standard library random number generators. So these are widely used for stochastic simulation. Examples of applications are in finance. Again, that's the area I come from. Branching processes in cancer growth and treatment modeling. Reliability testing in aviation and aerospace. And so, Lloyd, you probably know a thing or two about that.
Been there, done that.
Simulations to test whether buildings will hold up in the event of an earthquake. Particle physics. And computer graphics for video games. And where this comes in is in video games, you have backgrounds. You have mountains, trees, sky, clouds, and that sort of thing. And so you can use random number generation to vary that so you don't get the same thing in the background like you do when you're watching the Flintstones. So.
You know, I never noticed that until now. Now you're doing Flintstones for me.
I'm sorry. Okay, so the way these work is for a given seed, or more generally state initialization, you can generate a deterministic series of numbers that look random. So these aren't actually random, but they look random. And then they can be drawn as if they were being drawn from a particular probability distribution. So they would follow the frequencies as if you were drawing from, say, a normal distribution, which is our example here. So if you look at a standard normal distribution, you take sigma to be 1 there. What we can do is we can draw random numbers so that if we were to plot them in a thinly binned histogram, you would get something that looks like that. Okay, so just apologize, actually, what I'm seeing here is not what I usually see. I don't see the one step ahead. Instead, I see the next slide. So please excuse me, I might be a little bit messed up here. But anyway, so again, these were added to the standard beginning with C++ 11. And they were adapted from the Boost random number generator library, which still exists. So again, the purpose is to generate random numbers from a particular distribution, for example, normal, chi-squared, Poisson, Bernoulli, F distribution, T distribution, that sort of thing. So what this will do is generate a deterministic sequence of random looking numbers based on a seed value. And the advantage of this is for any seed value, each time you run it, you will get the exact same sequence of random looking numbers. So this is advantageous when you're developing. So as you go through step by step, you can see, okay, I'm getting what I expected each time. Or in the case of regression testing, you can test and you have targets you can measure against and make sure that your program is still doing what it's supposed to do. Disadvantage is it's reproducible for a known seed. And it's for this reason, you should not use these in cryptography. Those types of random number generators, though, are going to be a lot slower than what we're dealing with here. Okay, so the way this works is the setup is divided into engines, and these are a stateful source of randomness. So they're function objects that will generate unsigned integer values that are uniformly distributed. So that means the probability of any one of those numbers being chosen is the same as any other number. And then the distributions will take those positive integers and transform them into random numbers that are distributed, again, according to the distribution that you want to sample from. So if we look at this visually, you have an engine object. It's going to spit out positive integers. These will be then input into your distribution object. A transformation will be applied, and then you will get values that, again, they look like they've been drawn at random from a particular probability distribution. Okay, we'll look at just a few engine examples. I won't go through them all, but just to give you some contrast. Oh, that's nice. Okay, I'm gonna have to wing it here. If you could see the period column, you would see that for the first two rows, well, the first row is the default random engine, and it's implementation dependent. So it can be different on different platforms. It turns out, though, in the Microsoft compiler and GCC, it's just an alias for the next row down, which is the linear congruential generator. Now, the disadvantage here, which you can't see, is the period is very small. And so what can happen is after a certain number of numbers are generated, you can then get a repetition of the sequence. So that's not going to be very good if you're trying to simulate randomness. Yeah.
Got one question. You say very small. How small? So is it like 4 billion or much bigger or much smaller? Sorry, I didn't mean to make you have to reach for.
Actually, I just realized I could look over here for the information. Okay, so the period for the linear congruential engine is 2 to the 31st power minus 2.
Okay, so it's really close to 4 billion then.
Okay, but the advantage is it's fast. And so if you're prototyping a model or something like that, it's perfectly fine. And it's stuff that, again, my experience was done. You know, if you just want to get, you know, again, get the model prototyped. But then when you go into production, you'd want something with a higher period. Next on the list is the Ranlux 48 generator. And the advantage here is, if you could see it, okay, it has a period of 10 to the 170th power, which is very large. But the downside is it's going to be slow. Kind of the Goldilocks of the standard library for random engines is going to be the Mersenne twister. It's got an enormous period of 2 to the 19,337th power minus 1, which is a Mersenne prime number. And its advantage is it's going to be faster than just about everything except the linear congruential. Then there's a new engine that is going to be released with C++ 26. I should have mentioned up until now, each of these that I've mentioned, the way it works is you call it, there will be a functor, and you call it, and it will give you the next random value, and the next one, and the next one. With this new one, the Phyllox 4x64, what it does is it just generates all the numbers at once. Sometimes it's said to be stateless. It's not really, because it still requires a key value, kind of like the seed. So, but you might see that in the literature, so to speak. Yeah.
So when you say it's generating them all at once, it's generating like a huge block and then just
Yes.
storing it in memory. So you're paying a high startup cost for a very rapid runtime. Is that kind of the trade?
I'm not,
It can't generate all of them because if it's got a big period, it won't fit in memory.
well, it's not going to generate all the,
Yeah,
The
it's
entire
generating a
period.
batch.
yeah.
If you generate a big batch.
Yeah.
So, yeah, well, my next point will
Okay.
maybe make it clear. So the advantage is that this is going to be faster for parallel applications like on SIMD or stood async tasks, that sort of thing. So you just generate a pool of them. And so if you need, say you've got, you say you've got 100 tasks and you need 100 random numbers at a time, you just say, okay, take 0 from 99, that goes into
that
one
makes
task,
sense.
100 to 199 into one, and so forth. I have not had a chance to check this out, but hopefully soon. I'm not sure what the status is right now as far as getting a release of C++ 26, but I just haven't really tried yet. Its only downside is it's probably not going to be as fast as the Mersenne twister on a single CPU. Okay, moving ahead, looking at the distributions that are available. There are 2 uniform distributions. There is a discrete uniform and a continuous continuous uniform, which are represented in the standard library as int and real. There is the Bernoulli family, which includes the Bernoulli distribution and the binomial distribution, which is a series of Bernoulli trials. So, for example, you toss a coin 100 times, has equal probability heads or tails. You could use it to get the probability that you throw, say, 200 heads in, 25 heads in, say, 100 tosses, something like that. There's also the Poisson family, which includes the discrete Poisson distribution and its continuous analog, the exponential distribution. Also, there's the normal family. I really teed that one up. I was going to say probably none of us here comes from a normal family since we're C++ developers. That'll be on the next slide. And then there are 3 non-parametric distributions. I'm not going to get into these any further, but there are 3. There's 1 discrete and 2 that are you can form a continuous distribution from. So if you have any non-parametric applications, these are options that you can use. Okay, so in the normal category, there's the normal distribution itself, the log normal distribution, which is the log of the normal random variable. Chi-square distribution, which is, you think, I mean, at its core, the square of a normal random variable. The Cauchy distribution, which is like the normal, except but it has no defined mean or variance. So it's kind of it's an interesting distribution. Then there's the student's t distribution and the F distribution, which are used a lot in forming confidence intervals and in hypothesis testing. So how do we get these things to work?
Yeah.
Our first
Pardon me
example-
for interrupting, but there's someone waiting in the library. Okay, got it.
Oh. Oh, somebody was able to let him in? Okay. I actually can't see the screen, so let me see if I can pull this guy over here. Okay.
Okay, so we'll just use default random engine. You create it by giving it the seed value in as its constructor argument. And then we'll just create a, then you can actually see what it generates. This is not of any practical use to us, but you can see the integers that get generated by calling the functor. And so if we just go through this 10 times, you would see if you're using Microsoft compiler, this is what you would get. But again, this as well is implementation dependent. So on GCC, for example, you would get different values. But at this point, these are just the uniform positive integers, which will be used as inputs to the distribution. As an aside, though, I mean, the grand scheme of things, it doesn't matter because when you're working with random numbers, randomness, you're going to be using a lot of them. It doesn't really matter exactly what they are. However, if you do need to have consistency across platforms, then you might want to look at Boost because there's just one implementation and that's what you get. So you'll get the same results. Okay, so let's look at how we put this together with a distribution. So let's look at a continuous uniform distribution on the interval 0 to 1.
Oh, Robin's got his hand up.
Oh,
Bob's got his hand
yeah.
Okay, the standard says, I mean, I use these a lot. And the
Oh,
standard
okay.
says that of the named distribution, not the default distribution, but of the named distributions, they are supposed to be consistent across platforms for the generator, not for the distributions.
That's interesting because this is a counterexample. I mean,
Well, that's because you use the default, and which one is the default
No.
is not standard.
it's the same. If we go back here, this is the same as linear congruential on both Microsoft and GCC. At least it's supposed to be.
Linear congruential involves some parameters that set it up. There's a very large number of linear congruential generators, and it doesn't have to be the same one. There are
Okay.
two parameters for each linear congruential generator, and not all of them are good. Most of them are not.
Okay, that's an interesting point because I mean the way it usually works in C++ at least, you give it a single seed
Yes.
as the constructor argument, and so there's not. I'm not really sure how you would tweak it, but okay.
Yeah,
well,
yeah, but
that- that's-
the general definition of a linear congruential operator is the previous value times some parameter plus some other parameter modulo 2 to the 31 or whatever. And so you've got two parameters in general. So for a linear congruential operator, I'm sure you've got a couple of parameters that you can set. Although there are specific ones that are recommended that are good,
Okay.
and those are the default ones.
Okay. I'll have to go back and look at it then.
Yeah.
Okay, so anyway, back to our distribution. So in continuous uniform distribution on 0 to 1, we'll create a vector of size 10. And then you can see here, we can populate the vector by generating the next random number in the sequence. And the way you do that is you call the functor on the distribution object, and you give it as its argument the random engine that we defined in the previous slide. And again, I compared this on Microsoft and GCC, and they were again different. Okay, next example is a standard normal distribution. It's used a lot. Here, though, we'll use something a little bit different. It is possible to get a random seed, and it uses the operating system kernel and your hardware. So it uses entropy. So if you want a completely random seed, this is an option to you. You can use the random device class. So we just create an instance of it. And then similarly, you can't really see it because this animations are messed up, but you call the you can really see it, the RD functor here, and it will give you the next random value. But again, this is actually randomized. So then we can create a standard normal distribution, as you see here. Parameters 0, and 1, mean 0, standard deviation 1. And then again, we'll generate 10 normal variates and put them into a vector. And again, you just, it's really off, but you can see you call again in this case, the normal distribution functor, and you give it in this case, the Mersenne twister engine that we defined up at the top. And if you output them, when I ran it, this is what I got, and then you run it again because it's a different seed, you'll get a completely different sequence. Now, how can we use this stuff? Oh, back up. Also, for continuous distributions in the standard library, the default type is double, so you can just leave the template parameter blank. And also for the distribution, this default is standard normal, so you don't have to put in the 0 and 1 if you don't want to. Okay, so how can we use this? Here's a fun little problem. Let's recall the show, Let's Make a Deal. I think some of us here are of the age that we might remember this on TV from the 60s and 70s. And I'm gonna have to kind of go to my other computer here because I need my notes. Yeah, so there he is, Monty Hall. And one of the contests is, okay, so a contestant would be chosen from the audience, and there's a contest, there would be 3 doors marked, door number 1, door number 2, and door number 3. And so behind one of the doors was the prize, such as a new car. Behind the other 2 were zonk prizes, such as a goat. So in that case, you lose. So when the contestant would make a choice, say door number 1, Monty would then have one of the other doors opened. I mean, that is, so you choose one, then he'd have one of the other doors opened and would reveal, say, a goat. Then Monty would ask the contestant whether he or she would like to switch the choice to the other door. So the contestant chose number 1, opens door number 3, there's a goat, says to the contestant, do you want to switch your choice to number 2? This gave rise to what became a somewhat famous math problem called the Monty Hall paradox. And that is, if you were given the chance to switch, should you? I'm sure Bob knows. Anyone else?
And important assumptions, the host must open a door no matter what, and it must be one of the goat doors. Like that those are built-in assumptions in this problem.
Yeah, it's not at random.
Yeah. Yeah, but that's not like, oh, Monty might only sometimes open one of the doors or something like that.
Oh, no, it's,
Yeah. So based on those rules being set.
okay. Anyone? Sure.
Yes, you should always change.
Yeah, it turns out, yes. And your probability of winning the car actually doubles to 2/3. So it's kind of a non-intuitive result. There's an history behind this is there's an article written by a columnist, not a mathematician, but named Marilyn Vos Savant in Parade magazine in 1990. And this was published, and she said that, this is the case. And apparently, actually, there were some fairly well-known mathematicians who wrote and said, no, you're wrong, this can't be. Well, turns out she was right. So yes, you can show it using Bayes' theorem. There are some other explanations, and there's a good description in the Wikipedia article, which I've made the link below there. The way we can demonstrate this in C++ is what we'll do is we'll define 2 distinct Mersenne twistor random engines with different seeds and 1 uniform distribution, discrete uniform distribution on the set 1 through 3. And so that means the probability of any one of those numbers being chosen is equal to any of the others, so 1/3. So let's see. Sorry, again, my PowerPoint animations are getting messed up here, but is there a pointer, but I guess you can barely see it, but anyway. So one engine will correspond to the position of the car and the other to the contestant's choice. So we're going to just run these randomly. And then we have our discrete uniform distribution on 1 through 3 here. We have a counter wins, so said initialize it to 0. And then what we'll do is we'll break this up into 2 parts. We'll look at the case where the contestant does not change the choice and where he does change the choice. So the first one is quite simple. Randomly choose the door, randomly choose the position of the car. If they're equal, the contestant wins. We increment the variable here. And if you run this, say 2,500 times, you'll get about 33%. Reset the counter, and now we'll look at the case where the contestant does change the choice. And so the car can only, if door number 1 has been chosen, then the car can only be behind door number 2. So the only way that the contestant is going to win is if his original choice was incorrect. So he switches. So incorrect switches and increment the win. And this actually does come out to about 67%. And I had the output here somewhere. There we go. So yeah, I get about 32% and close to 67%. Okay, now we will move into boost statistical distributions, although I will probably refer to them as boost probability distributions. Because just try saying that fast 3 times.
Just call it BSD.
Yeah, or you could do that.
BSD.
Or, yeah. Or just try saying it fast once. I dare you. Okay, so these are not random. And also just to make a distinction, there are these probability distributions in Boost. There are also random number generators in Boost, which is a separate library. These are just going to give us the calculation of the probability density function, or PDF. So there, see, I can use initials. The cumulative distribution function, or CDF, and the quantile function. And this is available for a wide variety of distributions, actually 34 in all. These are provided as, these 3 functions are non-member functions common to all the distribution types in Boost. So it makes this really easy, really straightforward. And so we'll just look at an example next to demonstrate it. But, okay. So we'll look at using the student's T distribution and normal distribution. So this is probably not, okay, sorry. Okay. When you use these, so you need to include the header for each individual distribution. So we've got, as you can see, students T and normal. So it's very easy to construct a T distribution object, say with 4 degrees of freedom. And just the argument is the degrees of freedom. Or for a standard normal, again, the arguments are 0 and 1. Although, again, it defaults, so you don't actually have to include those if you just want the standard normal. To get the PDF and the CDF of the normal distribution, all you do is you call the PDF and CDF functions, give it the distribution object name and the value of X at which you want to evaluate the function. So it's just really easy, really straightforward. Why can't everything in Boost be like this? And for the T distribution, it's similar. You can also compute the quantile functions. So if you want it's actually percentile, so the 5th percentile, again, you just give it the distribution object name and the probability, and it will give you the percentile. And similar for the T distribution.
Is it estimating these empirically by running the distribution, or solving it symbolically?
Well, for the PDF and CDF, those are closed form solutions. For the quantile, as I recall, it's numerical. Maybe Bob knows for sure, but that's what I remember. I haven't actually looked at the code.
Yeah, it's probably numerical in that you're solving the inverse equation given the forward equation. So, but there are no random numbers in that.
Oh, that's right. Yeah, there's no randomness here. But yeah, I should mention too that, and this will come back here momentarily, that the quantile function is the inverse of the CDF, which is convenient to have. Okay, so these are all on the Boost website, but I put them here for your reference. So as mentioned, there are 17 closed form distributions in the standard library, and there are 34 in Boost. So the question comes up, what if we need a random number generator from the distribution in Boost, but is not in the standard library? And the typical problem is where you have data that exhibits skewness and or kurtosis. So kurtosis meaning the fatness or the thinness of the tails as you go out to the extremes of the distribution. And this is again, my area of finance, this is a very typical problem, especially the fat tails. So just looking at kurtosis first, no, it's not a disease.
Put it in your definition.
Yeah, yeah. Doctor, I got this kurtosis in my back. At the top, there's a standard normal distribution, and then at the bottom is, you can see it in blue. You might notice, I'm sorry, and the red one is a T distribution with 7 degrees of freedom. So you can see the T distribution has fatter tails as we come out here to the left extreme of the distribution. In finance, a lot of times you're looking at what is the maximum loss I could suffer at, say, 95% confidence. So that would be at the 5th percentile here. Well, if you're at the 5th percentile, say you cut it off, well, let's say it's there. You can see the normal distribution is going to underestimate the loss. And financial returns do exhibit kurtosis as well as skewness. So there is a distribution in Boost called the non-central T distribution, which can fit both skewness and kurtosis. Come on, there we go. And this is taken from the Boost website, but you can see here are 2 examples of skewness. To the left is negative. It's skewed to the data skewed to the negative side, and positive skewness here. You don't really see the kurtosis, which is why I brought in the previous illustration. Okay, so what we can do is write our own class template. And this is going to look a lot like the distributions in the standard library. So we'll call it stood non-central T dist. And this will act like a standard library distribution function. The way it works is you generate random draws from a continuous uniform distribution, again, over 0 to 1, and we'll use the standard library uniform distribution for this. We can then apply the probability integral transformation theorem, or the PITT, which is a fancy way of saying we're going to feed the random uniform variates into the non-central T inverse CDF, which is the quantile function in Boost. And then the results will be random numbers drawn from a non-central T distribution. Okay, so we'll start with a distribution class template, very similar to standard library form. And again, we'll default the numerical type to double. I thought I put this in the presentation, but it's missing. It's in the sample code. A nice thing to have here would be a concept where we would require this to be a floating type. So anyway, let's look at the private members. Again, what we're going to be using is a continuous uniform distribution with this from the standard library. and the boost non-central T. The private member variables are nu, and degrees of freedom are usually represented by the Greek letter nu, and delta for the non-centrality parameter, which gives us the skewness. Then the constructor, you just take in nu and delta, initialize them, and then we use that to instantiate the non-central T distribution member on the class. For simplicity, we'll just assume we're using the Mersenne-Twister engine. You could make this even more generic if you wanted, but I don't think it really adds anything to the example. So then we define our functor, and it's going to take a draw from the uniform distribution, feed it into the inverse CDF, and that will give us the next non-central T random variate. And then it just, again, looks just like using a distribution in the standard library. So Mersenne-Twister engine, we create the distribution, and that's 3 degrees of freedom and a non-centrality parameter of minus 0.05. And then in this case, I've just written a lambda to return the next value. And then we'll use the generate algorithm and populate a vector. And your results will look something like that. All right. Just briefly, I thought we'd look at a couple of alternatives to the Mersenne-Twister engine. So again, it's generally considered the best option in the standard library, as this massively long period, and it's going to give you better performance than the other options in the standard library that will have a sufficiently long period. The downside to the Mersenne-Twister is its state size is very large, which makes its object size large, which means it cannot fit entirely into CPU registers. So this is going to require more cycles to move from RAM to cache to registers. And you're going to run into similar issues with the 32-bit version. There are 2 more recent open source libraries that offer, when I say potential improvements, and we'll see why in a moment, but one is PCG, which stands for Permuted Congruential Generator, and Soshiro, which is exclusive or shift rotate. I certainly do not claim to be an expert at all in writing random number generators. To me, it's a black box. But anyway, that's where the name originates. Any day now. Okay, so great, you can't see the table. All right.
Okay, one more time, see if it comes in.
Oh, okay, we got it, but
Well, we don't have the period again, which is. Let's look at it one more time and see if it comes in. Okay.
oh, wait a minute, it's still, no.
Okay.
All right. Well, I'll just have to read off the period. Okay, so the period for the PCG generator is 2 to the 128th. And so while it's dwarfed by that for the Mersenne-Twister, it's still an astronomically large number and is going to give you just about, I mean, it's going to be essentially infinite for, pretty much any practical task that you'll have. I don't know, maybe it'll change now with AI, I don't know, but it's still astronomically large, so you're probably okay. And as you can see from the table, both the, looking at the state size, this means that we can fit the engine into two 64-bit registers here and 4 with Zoshiro. But with the state size for the Mersenne twister, there's no way you're going to be able to fit that into the registers. Just showing how they work. It's, again, very similar to what we did before. There are various constructor overloads for these, but we'll just use the single seed argument just for example here. So you create the engine, you give it a seed, create a distribution, say chi-squared with 15 degrees of freedom, and then you can get the next random variate from chi-squared by calling the distribution functor with the engine input, exactly the same. And it's going to be similar for Zoshiro. Here I'm using the binomial distribution, 20 trials, say with a weighted coin with probability of heads 45%. There's sample code that will go with this. It'll be linked to the meeting website. So there are full examples in that. Okay, well, let's see if this works. Again, going back to my days in finance, working with things like structured products and variable annuities. You often need to, for Monte Carlo simulations, you have to have, you generate random price paths, say for equities or other securities. And some of these products can go over 10 years or longer. So for each point, you're going to generate a price randomly. And for that, you would use probably the standard normal, the distribution. And then there's another transformation for that, but that's beside the point. The main point here is that you could have annual time steps. So you'd have 10 random draws. Monthly, you'd have 120 draws, and weekly would be 520 random draws for each of 50,000 scenarios. It turns out that, at least in my tests, the results were mixed. Okay, well, glory hallelujah, we get all the numbers here. Let's see if the animations work. So, looking at the incumbent, the Mersenne twister, first running serially, 10 time steps per scenario. When I ran through this and ran a pricing model that uses these, I found that for PCG, I could do the same thing in about 18 milliseconds, and Zoshiro under 24 milliseconds. So there's a definite improvement there. But for a larger number of random draws, and then again for each of 50,000 random paths, we get the times you see here for using the Mersenne twister. But if you compare it, there's really no significant difference. And I suspect what's going on is the amount of time it takes to generate the extra random numbers and run the pricing model, that's going to dwarf the amount of time it takes to move the Mersenne twister in and out of the registers. Okay, next up, boost accumulators. We're coming into the home stretch here, so hope you're still with me.
27 minutes left.
Oh, okay. It should be fine.
Okay.
Okay, so Boost accumulators. It's a framework for incremental statistical computations. And so it deals with the concept of an accumulator, surprise, surprise. And what this is going to do is, given a sample of data, it's going to take, I'm sorry, given a set of data, it's going to take one sample at a time. And at each point, it's going to update whatever statistics you want it to measure. So a prime example would be mean and variance. So you've got a large data set and you want to keep bringing these in, and you want to get the mean and variance for each sample that gets added to the accumulators. Others are max and min, and then mean and variance, for example. If you can have one or more accumulators corresponding to each of these statistics, and so these are all grouped within what's called an accumulator set. Uses the following pattern. Again, you select the computation you want, so mean, variance, so forth. The user or the program will push the data into the accumulator set, one data element at a time. And then as it's updated, the values, say of mean and variance, can be interrogated by the program. The template parameters are as follows: sample, which means the type, in this case, we'll just use double, but you could have more complex data element types. Features, that means the statistics that you want to measure. And then there's an optional parameter weight in case you want to compute weighted averages or weighted variances. So again, I just said this, but and I'm sorry, I don't have the one step ahead here, so shooting in the dark a little bit. So to declare an accumulator set, say that's going to measure mean and variance, it would look something like that. So as template parameters, you give it mean and variance. And the type here. Once this is defined, again, the sample data gets fed in the accumulator, and then the statistics will be computed. Just stretching. So quick example, mean and variance of a data set. Again, you need to include the headers that correspond to each of those statistics. And like we saw in the previous slide, we'll just define an accumulator set called ACC, double type, and it will compute mean and variance. So push some data into the accumulator, and then you can look at the results. And conveniently, these are overloaded for the stream operator, so you can just output them to the screen if you like. Add two more elements, and then you can see the mean and variance get updated. One thing to note here is that the variance in this case is the population variance. So that means the sum of the terms in the variance are going to be divided by the total number of observations, as opposed to sample variance, where you would be dividing by n-1. Keep this in the back of your mind, because in the next example, this is going to change, which is rolling windows. And this means things like moving average, moving variance, and so forth. Again, going back to finance, suppose you have a set of 25 daily closing share prices. When developing automated strategies for algorithmic trading, the computing moving averages and moving variances is very common. So an example would be, suppose you have 25 share prices. And you want to get at each step the 5-day moving average and moving variance. So you go up to 5, it will give you that value. Then you go from 2 to 6, you'll get the statistics over that next window and so forth until you get to the end of the data set. Just to demonstrate this, let's see. We'll use a vector, but we'll pretend it comes in as input data, not hard-coded values. So again, you need to include the headers for both the rolling mean and rolling variance. And this is our data set. Again, pretend it's input, not hard-coded. Okay, we set up our accumulator set as follows. So we tell it that we want to compute rolling mean and rolling variance, and that our window size is going to be 5 observations. Just to demonstrate this, we'll load the first 10 prices into the accumulator set and then get results over the final 5-day period. So just using iterators here. And I've set up these other variables so you can actually see them in the output. So what happens is each time through, the next element of the vector gets fed into the accumulator set here. Just to see where we are, those are the first 10 prices. Then we can get the moving average and moving variance of the last 5, from the last 5 observations, which you see. And so you just call the rolling mean and rolling variance again, put in the accumulator set argument, and you'll get the result. But before I show you the result, for some reason, I don't know why, but for rolling variances in boost accumulators, it uses the sample variance. So it's going to divide by n minus 1 rather than by n, as was the case with just the variance accumulator. So if you ever use these, it's just something to watch out for. And then these are the results that I get. And just to verify, I asked Google Gemini and I verified that the results tie. The complete list of operators for accumulators is available on their website, but I put them here for reference. You can see over here, there are a lot of weighted statistics that you can also calculate. So that's that third template parameter. Okay, well now we're going to move on to a proposal for C++ 29. And I see Richard is here. He's the primary author of this proposal. So it is a proposal to compute basic statistics for values in a range. So it's P1708. So you know, these frequently arise in all kinds of different applications. They're available in other languages, Python, R, Julia, and so forth, but they're not yet in the standard. So the statistics that are defined for this proposal, there are 3 types of means: arithmetic mean, which is the usual sum divided by n. There's the geometric mean, which I had a screenshot of. There it is, where you take the product of the observations and then the nth root of the product. And then there's the harmonic mean, which looks like that. So you sum up the reciprocals of the observations, and then you divide it into n. There's also the population variance and sample variance. And there's also a separate function with boost accumulators. There's only a variance. So you have to take the square root yourself if you want the standard deviation. But for this proposal, thank you, Richard. You also give us the standard deviation. So, which will also be, will give you the populations and sample version. And similar for skewness, kurtosis, and covariance. Okay, so not included in this proposal are the median mode and quantile. As stated in the proposal, it says these have been deferred to a future proposal. Also, accumulators similar to boost were also originally proposed, but these have also been deferred as well. So just some simple examples. I'm going to generate 20 observations from a standard normal distribution. We know how to do this now. And to get the mean, it's just easy mean of the vector. Now for variance, you need to tell it whether you want the sample variance or the population variance. You can do this by adding a Boolean parameter true, which says compute the sample variance. If you want the population variance, you set it to false. There is a default though, which applies to both variance and standard deviation and to the other functions, where the default is to compute the sample version. And likewise for skewness. For kurtosis, there is an extra parameter. And this is, do you want the full kurtosis or the excess kurtosis? What this means is the excess over the kurtosis of a normal distribution, which is equal to 3. So it's just going to subtract 3 from the result. But if you want the sample excess kurtosis, you don't need to do anything. It's just the default. For covariance, we need another vector, so generate another vector of 20 elements. And here for the sample covariance, you just include the vectors v and u. Now there's one more hitch to this, I should say feature, which is very convenient. It also applies to all the other functions, and that is you have an optional parallel execution parameter. So if your data set is enormous, this could probably save you some time. And those are the results I get. Okay. Richard, anything to add, or is that?
Hello, thank you. Yes, wonderful presentation here so far. On the previous slide where you have the variance and standard deviation, rather than being a Boolean selection, at this point we allow a user to specify a delta degrees of freedom. Think of it as 1 over n minus d. You specify d, thus allowing you not only to have the traditional notion of the population and the sample, but any other sort of configuration you would like as well.
Oh, really? Okay.
We found that to be the case with some of the Python libraries. We wanted to ensure that we had that feature available as well here.
Okay, cool. All right. Thanks very much. Okay, so that brings us to our summary. And speaking of randomness and parallel universes, this is one of my favorite next generation episodes. References. I'm sorry. Again, I see the next slide rather than the next lines. So I apologize. Just some closing thoughts. As you can see now, between the standard library, Boost, PCG, and Zoshiro, and now with the basic statistics proposal coming in another 3 years, we have now and will have a much improved variety of options for probability and statistics in C++. And this is really wonderful speaking as one who had to do a lot of this before C++11. So the Mersenne twister algorithm, we had to get from, there's an open source version of it from the actual researchers who developed the algorithm. We used that. Some of the other things we just had to program on our own. Or we, try to convince our boss to, pay the money and get a nice commercial library. But now there's so much that's available in the standard and in external open source libraries that it's a much improved environment. It's true that C++ will probably never be as feature rich mathematically as Python or R or Julia and so forth, but it wouldn't hurt to add more. And just a few things in the probability realm that I'd kind of like to see would be to incorporate all the boost distributions into random in the standard library. And as we could see here, that's really easy to do. Very low hanging fruit. A bit more challenging would be to add a few more 4-parameter distributions. And these are a bit easier to work with than the non-central T. One is the generalized lambda distribution. Another one is generalized hyperbolic. And then there's one more is the skew T family of distributions. And in fact, some of those are actually more recent. And actually, some of the research was actually done here at the University of Washington, the Applied Math Department. Also incorporate boost-like accumulators. So Richard, hint, hint, nudge, nudge. It would be nice to have. So anyway, some references and items for further reading and viewing. First, a completely shameless plug, but technically, again, this was a reference for this talk, chapter 6 and 9 of my blockbuster, best-selling New York Times bestseller book, soon to be made into a major motion picture, which is why I'm already reaping in tons of money, and I'm going to buy a house on the shores of Lake Washington in my dreams. And also the Standard Library book by Nikolai Yosu is an excellent book. It's 15 years old, but I still use it. And in chapter 17, he gives really, really nice coverage of random number generation that was added in C++11. A few other things you might want to look at for particle physics. There's this simulation library developed at CERN, which is written all in C++. Also, I thought he might be here tonight, but I guess not. Rebo Zhang, a PhD student at, again, applied math at UW. His research area is cancer modeling. And he gave a talk at CPPCon a year and a half ago, just a half-hour talk, so it's not a major time commitment. But it's quite interesting. He shows how he used random number generation and task-based concurrency in the work that he's doing. And these branching processes can get very computationally intensive. And the time savings that he got, plus the convenience of having the random number generation was quite remarkable. So it's on YouTube, highly recommended. Then again, the proposal itself for P1708. And I found this site to be really useful for information on the random engines and distributions. It is in the Japanese language, but it's pretty much all C++, and also you can just hit the English translate button on your browser. And then for background on the new Phylox generator that's coming in C++ 26, this paper goes through some of the details behind it. So Anyway, if you'd like to reach me, here are my contact details. And so, thank you very much. And so we have a little time for questions.
Okay, that's a little weird.
I just saw that today and I popped it in at the last minute.
There's something about it, the longer you look at it, the more it gets you.
So, okay, well, thanks everyone for coming and thanks for the input from y'all and that's it.
Cool.
Cool.
Thanks, folks, and we'll be back next month. I've got a speaker lined up. I'm not quite sure who it is yet. Is it you? No?
Maybe. I actually don't remember when we agreed on, so it could be me.
Okay, I'll check and remind you if it is.
Sounds good.
Maybe I'll check and remind you even if it isn't. Okay, thanks, folks. I'm going to go ahead and stop the recording here, and we'll get this stuff posted on the website fairly soon.